Okay, so we're looking at this problem about pendulum, small rock with a mass 0.2 kilograms. It's fastened to a massless string with a length 0.80 meters. Okay, and swinging with a maximum angle of 45 degrees with vertical resistance is negligible. First thing we're going to find is what's the speed of the rock as it passes through the vertical position. Okay, so we're starting at this sort of position here. Okay, okay. There's our pendulum. It's an angle of 45 degrees, supposedly. Its initial velocity is 0. When it gets down to the bottom, we want to find out what is its speed here. Okay. Well, the best way to do that is to conserve energy. So at the top, when it's in the first position, at the beginning, we're going to say that whatever the energy it had at the beginning is going to be the energy later, or equal to the energy later, the law of conservation of energy. Okay. And so at the beginning, the only kind it's going to have really is GPE. And at the bottom, the second part, it's not going to have any GPE. It's going to fall as far as it can fall, and it's just going to have kinetic energy. And the equations for that are easy, mgh, and this is 1/2 mv squared. The masses divide out. The speed is going to be 2gh square root. So that part's not hard. The hard part of this problem is h. Like, how far did it fall? Well, it fell down from there to there. And how far is that? Like this distance here that goes from here to there. Well, if we take a look at the actual picture, okay, like this is where it starts at. Okay, if it starts here, this length L is the length that it has, and the height here is going to be, if this is 45 degrees, it's going to be L cosine of 45 degrees. And when it gets to the bottom, it's going to have the entire length. So that entire length is going to be L. So the difference, the amount that it fell, is going to be this distance here, which is going to mean H is going to be L minus L cosine of 45 degrees. So that's what H actually is. It's going to be, I'll write it over here, 2G, I'm going to factor the L out, 1 minus cosine of 45 degrees. Which again, if we plug everything in, it's going to be 9.8 meters per second squared, 0.8 meters, 1 minus the cosine of 45 degrees. And all of that, when you plug it in, should give you a number of about 2.1 meters per second. There we go. The next part of the problem, part B, asks what's the tension? Oh, hold on a second. Okay, sorry. Okay. What is the tension of the string when it makes an angle of 45 degrees with the vertical? So again, we're going to draw a picture of that. Okay, here is our pendulum string. There's our pendulum bob, and it's making that angle of 45 degrees with the vertical. Again, sorry for the 5 there, but you get the idea. Okay. Well, if we take a look, the centripetal direction, oddly enough, the centripetal direction, remember, is going to be this one. Okay. Or sorry, better still, this one, toward the center of the circle, maybe. There we go. It's going to be toward the center of the circle. Let's erase that because that annoys me. It's going to be toward the center of the circle. You can see I drew the arrow there to represent that centripetal direction. Well, that's kind of difficult, and it's kind of a pain, because what it means is we're going to actually have to balance the forces in that direction. If we look at the force diagram for this, it's pretty easy. It's just going to be this thing and this thing. This is the tension, and this is going to be mg. But the balancing isn't going to happen that way. The balancing is going to happen this way, where we have the component we care about is this one, because that's the centripetal component that we care about. The angle is 45 in here, okay. And we care about this one here. Okay. And remember that at this point, that it's not moving, so those two are going to be balanced. So what that means is that in this case, t minus mg cosine of 45 degrees equals 0. Okay. It's pretty tempting to say that t equals, and I almost did myself, to say that like t sub y equals mg. But remember, it's not balanced. It's not in equilibrium. Like if you let that thing go, it's going to swing back down. It's not stuck there forever. It's not stuck there for any moment in time. Okay. At this moment, it's a centripetal force. It's a centripetal acceleration. It's going to swing down there as soon as it can. Okay. So that's really what the force is going to be. So we can solve what the tension is. It's going to be mg, which in this case is 0.12 kilograms, 9.8 meters per second squared, cosine of 45 degrees, which all works out to somewhere in the neighborhood of 0.83, I think it is. Newtons. Next, we're going to take a look at part C, where we're finding out what the tension of the string is. It passes through the vertical. So it's hanging straight down here at the bottom. We want to find out what that is. Well, it's going some speed. Remember, we figured that out before. The velocity is 2.1 meters per second. So in this case, A is not 0. These are not balanced. There's going to be some centripetal acceleration upward because it's going in a circle. Okay. So when we balance it, we're going to have our force diagram. It's pretty easy. We've got tension up and we've got mg down, but you can notice that I didn't draw them as balanced or equal because they won't be. Tension has to be greater than mg, otherwise it won't stay in that circle. So in this case, t minus mg is going to equal ma sub c. And so I'm going to solve for tension. It's going to equal m, and I'm going to go ahead and put v squared over r plus mg, which in this case is going to be m, I'm going to factor out v squared over r. So, sorry, I should have just put the numbers in here. That would have been a lot easier. So let's do that. So it's going to be 0.12 kilograms, 2.1 meters per second squared, over the radius, which is going to be the length of the string, 0.8, plus 0.12 kilograms times 9.8 meters per second squared. I left the units off there. Okay. When you calculate all that out, the first term is 0.12 times 2.1 squared divided by 0.8. I got 0.66 newtons. And for the other one, 0.12 times 9.8. I got 1.17. So I add 0.66 to that. And I have 1.1.1